Our session this afternoon, bipolar junction transistor, and we're going to do a little bit on field effect transistors as well, but we're going to look at the basic construction and action of a BJT. We'll look how it can operate as a switch. Some point, maybe next week, week after, we'll look at it as an amplifier as well. Then we're going to have a look at the field effect transistor. All right, so can you all hear me? Because that's telling me there's something wrong with my audio. Can you hear me all right? Dom?
Yep.
Can you hear me all right? Because that's just told me there's something wrong with my audio when I don't think there is.
I can hear you perfectly.
Good. Right, so moving on. So, operation of a bipolar junction transistor, or BJT. What consists of, there's two PN junctions sandwiched together. So you've got two types that you can have. PNP, so what you got there is an N material sandwiched between two pieces of P material, like it shows on the left, right, sorry, called a PNP transistor. And then an NPN transistor, there's two pieces of N material with a piece of P material sandwiched between. Now, these things have got three terminals. One, if we look at the NPN type, because that's what I'm going to major on and just touch on PNP, but you've got the emitter terminal as one of the N type pieces. The other end of that is, the other N type is called the collector, and then the P type material in the middle is called the base. And you've got a similar action for the PNP, except the emitter and collector are connected to P-type material with N-type base in the middle. Okay, and then below each of those, you've got the circuit symbol for both NPN and PNP transistors. And you always have an arrow on the emitter, and the emitter points always from P to N. So your base on your NPN is P-type, your emitter is N-type, and the arrow is pointing outwards towards the emitter terminal. On the PNP type, the arrow is pointing inwards from the P-type emitter material to the N-type base material. Okay, everyone happy with that?
Yeah.
Yeah, no dissenting voices. Okay, so the action, the basic action of a BJT is that if we have a small current, IBE, flow in through from the base to the emitter, then we would have a much larger current flow from the collector to the emitter. And this is the action of it as a transistor and how it can be used both as an amplifier and a switch. So we can control the collector current by controlling the base to emitter current, and a little bit more about that shortly. Okay, everyone happy with that?
Yeah.
So what that means is we can use it in its most basic form as a kind of switch with a low current, signal current in the base emitter circuit as shown on the left. And then on the right hand side, we have a main current flowing from the battery down through this, what would be the load resistor at the top here, and flowing from collector to emitter. So we can use this signal current to turn this main current off and on. And again, we're going to gradually go through a little bit more detail on that. All right. And so just to show a little bit more, when we, the basic operation, we studied last time the PN junction diode. And we know that if we forward bias a PN junction so that it has at least 0.7 of a volt across it, then that diode will conduct in this direction and turn that lamp on. And we'd have 0.7 of the 12 volts across the diode. We'd be left with 11.3 volts across the lamp. So transferring that theory of 0.7 volts forward bias and PN diode junction to that of the transistor, if we make the voltage from base to emitter 0.7 volts, this voltage across here, then what happens is a much larger current flows through here, through there, and out there. So that's just another way of showing that. Okay, we're going to do now, if everybody's happy with that, is look at a video of what's going on inside those junctions with the chargers.
Are we able to watch the video by ourselves? Because last time it was quite bad quality going through Zoom.
Okay, yeah, yeah, of course you can do that.
Okay.
All right. So you're going to watch all. You're all going to start at different times and then come back. Yeah.
Yeah. I mean.
Should we just try it first? Because that might be better this time, Tom.
We can try it. Yeah.
I'll stop the share on my iPad for a minute. And I'll share it straight from my laptop screen. Okay. Just bear with me, sorry. I thought I already had this opened up. Right.
This right here is a
NPN. This is a
Right, let's just try and share it now.
a bipolar junction transistor, which is a pretty common kind of transistor. And this particular one is an Npn.
Can you hear that?
And so this transistor is made up of 3 layers of silicon.
Yeah, that's okay.
Like this. And maybe you can guess what it means with the Npn transistor. These 2 layers of silicon N-type, and this layer here is P-type, Npn. And if you haven't watched my previous video where I go into quite a bit of detail about what N-type and P-type silicon is, you should definitely go back and watch that. Otherwise, this is going to make a whole ton of sense. And so this is an NPN transistor. They make PNP transistors as well, but we'll just talk about that. And so this here is the circuit diagram for a transistor, and it's got the three leads coming off of it. There's a emitter, a base, and a collector. If you look at the actual physical transistor, there's three leads coming in. This is the emitter, the middle one is the base, and this is the collector, although that's not really standard, right? In this particular case, that's how it works. And what a transistor does is it is a current-controlled switch. And so what that means is that if we establish a small current from the base to the emitter in this direction, the transistor will switch on, and it will allow a very large current to flow from the collector to the emitter. And sometimes you can also use this as an amplifier. Small current amplifier, a large current flow here. And so first off, there's actually something kind of confusing about the way this arrow difference, which is the circuit diagram, and a lot of times a lot of engineers like to think about.
I'm not getting this too well, Mike.
Sorry?
I'm not getting it too well.
Hang on.
Really matter which
Right. Just let me. Okay, all of you. Can I ask you in a minute to all have a look at this video separately? So you use the link, okay? One thing to watch out for, though, is we always worked with conventional current flowing from positive to negative. But here, because of the way this works, he has to talk about electron flow in the opposite direction. So from electrons, current flow is actually electrons flowing from the negative terminal to the positive. So just try not to get too confused about that. But this was the best description of an NPN transistor operation that I could find that wasn't almost in a foreign language. Okay, so watch it, and I'll expect you back listening to me. Let me know in about 5-10 minutes. Yeah.
Yeah. So you want us to watch all of it?
Yeah, if you watch it all the way through, please.
Okay.
But when we start to actually look at what's going on inside, it's easier to think of this directly, instead of the convention. So really what's going on in here, even this way, and if you start going that way, in reality, the electrons are flowing from the emitter to the base. So we'll just turn all this around for this discussion here. And so to kind of restate what it is that the transistor does, in terms of a small flow of electrons from the emitter to the base turn the transistor on and allow a large flow of electrons from the emitter to the collector. So if you look at it in this scenario, this piece of N-type material might be the emitter. This middle P-type is the base, and then this N-type material over here is the collector. And so what we're going to do with the transistor is that we're going to try to put a bunch of electrons in over on this side, and we want to get them out over on this side. But if the transistor is off, then we're not going to get that current flow. And in order to turn the transistor on, what we want to do is get a small current flowing through the emitter and out the base like this. And once we get that small current flowing, then the transistor will turn on with a large amount of current here to flow all the way through it. So let's redraw this so we can kind of get a closer look at this. So if we take a closer look at what's going on here, we've got the emitter here, which is N-type material. And so we have these extra electrons that are here that are free to kind of move around. We've got the base, which is P-type material. So we have these holes that are in here that are free to move around. And then the collector is also N-type, so those electrons that are free to move around. Each of these PN junctions, remember we have this depletion region, which I'm kind of exaggerating here. We have this depletion region because the electrons from the N-type material are going to fill in some of the holes in the P-type material to neutralize each other. So there are no charge carriers in these depletion regions. And so what happens is if we want to try to get a current to flow through this thing, maybe we'll hook up, move up here. We hook up a battery here just across the whole transistor from the emitter to the collector. So this is the negative terminal, positive terminal. Thinking about electron flow here. The negative terminal of the battery is going to kind of inject some electrons into here. It's going to become a little bit negatively charged. So there's going to be a few more electrons that enter this area, and some of them might even kind of creep into this depletion region a bit if we get enough electrons to come in here. But we don't have a current flow here. We're not going to drop electrons out of the base holes here. So we're not going to see that diode action here. We don't have that 0.6 volt differential between the emitter and the base yet. So we might have some more electrons coming in here, but nothing crazy is going to happen here. At the same time, some of the electrons that are in the collector are going to be attracted towards the positive terminal of the battery. So we'll lose some of these electrons that are going to get kind of attracted to the battery. So really, nothing too exciting has happened here yet. No current is flowing, that's for sure. But now what happens when we try to turn on the transistor? So when we try to turn on the transistor, what we're going to do is we're going to try to apply a small current from the emitter to the base. And so we might have a small battery down here that we connect to across the emitter and the base. And so now if we just look at the emitter and the base, it looks like we have a diode, and we're kind of trying to get current to flow through it in the forward direction, forward bias of this diode. And so what's going to happen is the same thing that we saw when we looked at the diode in the previous video. Electrons are going to come into the emitter here, and we're also going to draw electrons out of the base. So draw electrons out of the base, we're adding holes here to the base. And as long as we get about 0.6 or 0.7 volts of current flowing in this direction, so if this is greater than about 0.7 volts, I think, for most transistors, then we're going to start actually getting current flow. And so these electrons are going to get close enough here that this depletion region will shrink to the point where we now have charge carriers all the way through here, so we can carry a charge all the way through. So now this is where things get really interesting. So we've got a bunch of things going on, right? So first, we've got lots of electrons entering the emitter over here from this battery here. But also, we've got electrons entering from this battery here. Second thing that's going on is the emitter part of the transistor. The way they manufacture these is the emitter is really heavily built. So there's a relatively higher concentration of the phosphorus atoms here. So there's a lot of those extra electrons that are free to move around anyway. So there's actually a lot of electrons here just to start with. Just the way they manufacture the transistor. And so all of this means that once this emitter to base current gets going, this current this way gets going, we've got a lot of electrons here that are just going to start wandering into the space. Diffusing. So we're going to have a lot of electrons that are going to start diffusing into the space. And some of them are going to fill in these holes, and a few of them are going to come out down here. But there's something really interesting, which is this base is really thick. That's the key. If the base were really thick, then they would all just flow down this way. But because the base is really thin, they're kind of close to this area here. And if you remember when we looked at the way the depletion region forms, the way the depletion region forms is there were electrons that were over here that went over here to fill in holes. And so this area, because the electrons have left, is positively charged. So there's this positive charge that happens here because we've got those phosphorus atoms over here. They used to have an extra electron, and we still have an extra proton, but that extra electron is going over here. So there's this positive charge here. There's a negative charge here as well to kind of offset that before the electrons win. But we have all these electrons that are just diffusing into the base. So lots of electrons are coming in kind of this way. And all these electrons that are bunched up, they're going to get just attracted to this positive charge. And so a lot of these electrons will actually just sort of scoot right through this depletion region and get attracted here. And then, of course, once they enter the collector, they're free to wander around just because, just the same way as any of these other electrons are free to wander around. And of course, there's this positive terminal of this battery that's going to attract electrons here. And so you get this action where you got all the electrons bunched up over here that are being drawn into the base by this little current. And once those electrons end up in the base, there's this really strong positive charge that's really close because the base is thin. The key here is the base is really thin the way they manufacture it. And so these electrons get drawn to this positive charge. They're already kind of moving this way, and they just get drawn right across. And then once they're in the collector, they're perfectly happy to wander. So it immediately sort of finish most of the electrons actually make that and complete this circuit. And so just the small amount of current going this way, just enough to kind of get rid of this depletion region in here, combined with the fact that you've got lots of electrons coming in from here, lots of electrons coming in from here, and the emitter, the way they manufacture it, is heavily doped already. As soon as you close this depletion region, they start moving into fusing into the base. Because it's so thin, because you got the positive charge here,
Just the small
99% of the electrons
going this way, just enough
into the collector.
combined with
Here,
the
there's also
here, lots of
here.
and
And that's how
here,
the
here, already.
right plug here
As soon as
turns
they
on the transistor and
close this depletion region, start moving into the fusing into the base. Because it's so thin, because you got the positive charge here, most of it swept into the collector, through the circuit. So just a small current.
It's 2020, the world's gone mad, and the team you manage is all over the
That's
place.
how the transistor works.
Monday.com will help you reunite your team so you can get their work back on track and keep everyone aligned. Bring all your workflows.
Right, boys. Right, so anyway, moving on to the next page of really isn't my day, is it? So this transistor then can have be in three different states depending on what you're trying to do with it. The three basic states are that you can have an active region. That's where you'll have the transistor operating in a state where it can adjust the current IC up and down according to how much current you pass into the base. So we'll cover that in more detail in a minute, but this Greek letter beta here is the current gain of the transformer. So more about that in a minute, but your collector current is your base current multiplied by the DC current gain of the transformer. And then you have two regions where one called saturation, that's where the transformer is turned fully on So acting as a switch, it's just like closing the light switch. You make the transformer saturate and turn on fully. And then you've got what's called cutoff. That's where there's less than 0.7 of a volt in your base to emitter junction, and you have no current flowing in the collector. That's the fully off condition. So they're the three general states for a bipolar junction transistor. So when you want to operate the Npn transistor as a switch, you have to set what's called or as an amplifier actually, but there's a bit more to it when it's an amplifier, to set up what's called the DC operating conditions or the bias. So what we'd first do is apply a voltage VCE to the collector emitter terminals, such that on an Npn transistor, you got the positive to the collector, the negative to the emitter. Okay. Yeah. Everybody happy with that?
Yeah.
Yeah.
Yeah. Good. Then, to turn on the transistor, we've got to apply a positive voltage to the base between the base and the emitter. And this configuration for this transistor, there are two other configurations, but this is the most common one, is that it's called the common emitter because the emitter is common to both the input over this side and the output over this side. Yeah, so there's a common, there's the emitter, and it's common to both input and output of the transistor circuit. So if we apply a voltage of at least 0.7 of a volt here, VBE, then the transistor will turn on and we'll get a current flow from
Good choice.
this side, current flow through the transistor, and we turn the LED on. So just by controlling this small voltage here, we can turn that LED on and off. Okay? Yep. So a little bit more then about the current gain. So when we connect this NPN transistor in what's called common emitter mode, so the emitter is common to both the input and the output, transistors turned on with a V base to emitter of 0.7 volts. This would see a current IB flow into the base and cause a much larger current to flow in the collector. So by Kirchhoff's law, we've got current IB going in here. We've got a current IC coming in at the top and an IE coming in. So if we treat that like the node of a circuit, there's IB, that's coming in. There's IC, that's coming in. And then IE going out is at the bottom. Remember what we always do, all the ingoing currents are on one side and all the outgoing currents are on the other side of a Kirchhoff's law equation. So IE must be IB plus IC. Yeah. So the ratio between the collector current IC and the base current IB is called the DC current gain beta of the device. So if we want to find beta and we can measure both IC and IB, beta is equal to IC divided by IB. You can find the beta value on device data sheets. In some cases, that's called the HFE of the device. That's a bit of an older term for it. These days, you'll find it's called beta. The value of this beta can vary from about 20 for high current power transistors to well over 1,000 for high frequency, low power type bipolar transistors. The value of beta for most standard NPN can be found in the manufacturer's data sheet, but generally it ranges between 50 and 200. I do have to say though, for two given transistors of a particular number, so two BC109s or something, you could have very, very different betas for each of those transistors, and yet they're supposed to be the same. It is quite a variable function of the transistor, the beta. There are ways around controlling that, but for most devices, it is quite variable, even for a device of the same name number. All right. Any questions about that?
No questions.
Good. So, NPN transistor, example 1. Bipolar transistor has a DC current gain. Beta is 200. Calculate the base current, so IB is a question mark, required to switch a resistive load of 4 milliamps. So IC 4 milliamps. How are we going to go about doing that?
Taylor?
How do we calculate beta from the previous page?
From the previous page, we oh, I've lost it. Where was I?
The gain is how much bigger is the collector current than the base current?
Is it IC over IB?
Exactly. IC over IB. So we want to know what IB is, so we can rearrange that, can't we? IB comes up top, IB is equal to IC over beta. That's 4 times 10 to the minus 3 over 200 equals.
I'll whack it in my calculator. 1 sec.
You whack that in your calculator, don't.
2 times 10 to the negative 5.
Yeah, convert that to a value of -6 then.
Eh?
What?
Well, you want it as 2 times 10 to the minus 5. If we can make it times 10 to the minus 6, that'll be microamps, won't it?
Oh, right, yeah, so
Yeah.
20.
20 times 10 to the minus 6 amps equals 20 microamps. So you're putting a tiny little 20 microamps in at the base and getting a current of 4 milliamps, 200 times bigger, flowing in the collector. Yep. Okay. On the next page, we now consider one other point to remember about the bipolar NPN transistors is the collector voltage, VC, must be greater and positive with respect to the emitter voltage to allow current to flow through the transistor. So, furthermore, there's a voltage drop between the base and emitter terminal of about 0.7 of a volt. We know that because that's the forward bias that we need to turn that part of the transistor on. So the base voltage of the NPN transistor must be greater than this 0.7 otherwise. So we've got this resistor RB, we're saying here, in series with the base. We must have, if we drop 10 volts across that, it's not very big, but we must have, for it to work, 0.7 across there. You must have 0.7 base to emitter. So if the volt drop across RB is 7 volts, we must need to input at least 7.7 volts at the battery here. Yeah, because that current is going to drop 7 volts across RB, leaving 0.7 volts across base emitter junction. Okay, so from that, IB we can calculate from the base voltage that we're putting in from the battery here, take away the 0.7 or whatever else it is, base to emitter, divided by the series resistor. That way we can limit the series resistors there to limit the base current as necessary. All right. Everybody happy with that?
Splendid.
Yeah. And so if we gradually increase VB so that IB gradually increases, we'll reach 0.7 volts across the base to emitter junction. And then from that point, the collector current will start to rise exponentially up to its limit. Yeah?
Yeah.
So example 2, NPN transistor has a DC base bias voltage of 10 volts. So we got this 10 volt battery here, okay, and the input base resistor is 100k, this one here. What will be the value of the base current into the transistor? So how can we calculate that?
Base current. So there's a 10 volt power supply going across a 100 kilo ohm resistor. So you just use Ohm's law to work out the current.
Yeah, but remember we've got to have 0.7 volt drop here. Yeah.
All right.
So therefore, this must be 9.3. Yeah. So IB, as it says on the previous page, is the applied voltage at the terminals VB, take away VBE, which is the 0.7 for a silicon transistor, divided by RB. So we got 10 volts minus 0.7 divided by 100 times 10 to the 3. Anybody put that in a calculator?
I'm on it.
Have the answer in microamps, please.
10, 100 times. Uh, 93 times 10 to the -6.
Yeah, so it's 93 microamps. Yeah?
Yeah.
So having a series resistor in there is a way of additional way of controlling the current and the voltage to the base emitter of the transistor. All right?
Yeah.
Okay. So we've majored on the Npn transistor, but just to make sure for completeness, we consider the PNP. Much of what's been said, the principles of operation of the Npn transistor, is also true of the PNP type. To turn the transistor on, you still need to have a voltage of 0.7 volts across the base to emitter junction. However, the base now has to be negative with respect to the emitter, as shown below. So you can see that the little VB battery is the opposite way round. So the base terminal is negative with respect to the emitter terminal. Okay, and the emitter is also positive with respect to the collector. And so we get the collector current flowing through from the emitter through the transistor and out into the collector and through the load in that diagram. Okay. Yeah. So sometimes the way I like to think about it is, if we just nip back to the previous slide, the NPN transistor is a switch turns to sit on top of the negative rail, the 0 volt rail down the bottom here. So the emitter sits on the 0 volt rail. With the PNP, the emitter hangs from the positive rail. Yeah. With the negative rail being the 0 volt rail being down here.
Mm-hmm.
All right? Yeah.
Mm-hmm.
And then what we have to consider is the current. So as we've got a negative connected to the base, the conventional current is flowing out of the base. Yeah. So therefore, in this case, IC has to be, if we draw that node thing again that I did before, we've got IE flowing down and into the node, IB flowing out that way, and IC also flowing out. Yeah. So if we again write that IE is equal to IB plus IC. Therefore, the collector current is the emitter current. Take away the base current in this case. Yeah.
Yeah.
Whereas in the NPN, the emitter current is the collector current actually is still the emitter current, because the emitter current in the NPN was the IB plus IC, wasn't it?
Was it?
Yeah. Yeah.
Oh, I might have missed that.
Let's go back to it. Yeah, IE is IB plus IC. It's just a slightly different way of thinking about it because that IB current is flowing out instead of in.
Gotcha.
Yeah.
Just to double check. So obviously I don't have a printer at home, so I'm not able to print out these workbooks. But are these being on Moodle with the workings out? Because obviously I'm trying to work along, but I'm not able to draw down each diagram.
This is why I was struggling this morning. I couldn't get my notebook file up on the iPad. I've got the notebook file on the iPad. That will be exported as a PDF when we're finished and put up on Moodle.
I think
So
I struggle.
So
I struggle opening PDFs.
Yeah, on Moodle, I will put the blank notes that I've sent you. Yeah.
The what? Sorry.
The blank handouts that I've sent in case anyone's missed them.
Right.
Any copies with worked solutions in them to detailed problems.
Yeah.
Plus a PDF copy of the ones that I've written on during the session.
Yeah, because they're really useful.
Yeah, because they got all the scribblings on the drawings as well and everything that won't be in the worked solutions one. You see.
Yeah, that's it. Yeah.
All right.
All right, gotcha.
So you might ask, why do we bother to have two different types, NPN and PNP? Well, there are plenty of NPN transistors available. Why have two different types? Well, what you can do, it's more when you're working with it in amplifier mode that you'd want two different types. But what you do in a particular type of amplifier, maybe we'll cover it a bit later, is you have an NPN matched with a PNP. And if you take an AC signal going in here, one transistor handles amplifying the positive half, the NPN one, and the PNP one amplifies the negative half. They work in what's called push-pull mode. Yeah. So you can better amplify, and you get less distortion and all that kind of thing by using two. Also, there's another circuit. Then I don't know if I'll get a chance to cover it, but where you have two transistors in what's called a Darlington pair. So you actually amplifying the signal once and then amplifying it again. So you get a much bigger current amplification and voltage amplification out of two transistors than you do one. Okay.
Yeah.
Yeah. Right. So we've talked about this transistor as a switch. It's very simplified at this stage, but this one of the major applications of transistors is for this on-off switch situation. We get to digital circuits. So some output devices, such as LEDs, don't take very much current, and so you can switch them directly. What's that?
What's that?
Who did that? switch them directly from logic gate circuits, which are essentially transistors. However, if you have high-powered devices like motors, solenoids, high-power lamps, etc., then you'd use a transistor to switch them off and on. The other advantage that offers over relays in terms of speed of operation, so they operate much faster than a mechanical switch, and also transistors don't have the mechanical wear, so a finite lifetime on the wear of the mechanical parts like you would for a relay. Yep.
Yeah.
Now, in detail, we'll look at this diagram, okay, the operating regions. Don't worry too much at this point in time about that dot in the middle that says the Q point active region. We'll come to that when we look at amplifiers, all right? But we will as a switch, we're interested in these two regions. So you've got the saturation region on the left, which represents the transistor. So if we're operating in that region, we're operating in saturation mode, and the transistor is fully on. And the transistors, when the transistor is fully on, you've got the maximum IC flowing. So you would set it up. In this case, we're looking probably about here. We're looking at about 80 milliamps flowing. Okay, and that comes from the supply voltage VCC divided by the load resistor RL in the collector. All right, and then down the bottom, you've got a pink region, which is where the it's called the cutoff region. That's where the transistor is fully off. Okay, so that's where the collector current is 0, and the voltage across the collector emitter is the supply voltage VCC. So we want to, when we set up a transistor as a switch, we want it set up to operate between these two regions. Down here is completely off, up here is completely on. All right, these curves that you see here, 1, 2, 3, 4, 5, 6, they are the curves for different IBs. Maybe IB is 10 milliamps, 8 milliamps, 6 milliamps. So for different applications of IB, we can get different curves, output curves from this transistor. All right, but for the time being, we're interested in the fact that as a switch, we want to operate between the maximum IC current and 0 IC current, on, up here, off, down here. Yep. No dissenting voices.
Yeah, cool. I'm back.
All right. So, cutoff region. At the cutoff region, yeah. Yes.
Oh, is that someone
Look
writing
at
on
the
your screen?
diagram. Look at the diagram. Cutoff region. So we collect the input V in directly to 0 volts. So we'd have no voltage across the base to emitter junction. Yeah. It's less than 0.7. Therefore, it's reverse biased and the transistor is turned off. It's fully off and in the cutoff region. So we get no collector current flow. It's like having an open switch down in that bottom leg over here. We've got an open switch there. Yeah. So no current in this condition, no current will flow through the load resistor here. So you all agree and see that. Yeah. But this V8 voltage will sit at VCC. So if we was to measure this voltage here, we'd get whatever VCC was. because that switch is open. Yeah? Everybody happy with that? And then in the saturation region, so if we connect the input to VCC, we'll have a base emitter voltage at or greater than 0.7 volts across here, yeah, which will turn the transistor on. So it's like closing this switch down the bottom here, this one, and therefore we'll get a current down through the load resistor. Yeah, we'll get a maximum collector current equal to VCC divided by our load. Yeah, or we'd have a voltage across here of 0 volts, but VCC across the load resistor. Everybody understand that? So it's operating as a closed switch.
Hell yeah.
Yeah. No other dissenting voices? I'm not hearing many other people say, yeah, you understand it.
I'm all you need,
Connor?
Mike.
Hello?
What?
I've had my mic on mute for ages.
Who's that?
Connor.
Connor? Yeah.
Yeah, I didn't actually realise.
You
Have you been-
absolute
have you been-
numpty.
Have you been saying that you don't understand anything then, Connor?
No.
Are you okay? Are you?
I think so. Well, yeah.
That's- I'm just mindful that this is a difficult situation for everybody to be able to talk up. So I'm pausing. If anyone wants to say they don't understand anything, then please do say so. All
Yeah.
right. Right. So, example, right? Transistor switching circuit to control a high power circuit. We've got a high power load that we want to connect. What we can do is connect a relay that will switch the high power load to a transistor. So we can turn an input on and off, turn this transistor on and off, and operate that relay to an output. This is kind of what you can have as proximity sensors and electronic sensors on a machine that are actually transistor outputs that will operate relays. The one thing you need to do if you're operating something like a relay, which is essentially that relay is a coil, you have to remember back to when we energize a coil, and when we de-energize it, we get this so the current's going through it and it suddenly drops. Remember, we get this large reverse voltage in the inductor due to Faraday's law and Lenz's law. What that can do is send a large current back through the transistor and damage it. So we get this what's called a flywheel diode. So
I think
instead of a
Macaulay
large
asked a question.
Macaulay,
Yeah, he asked a question.
So I missed, what was that law? Faraday's law.
yeah. Remember with the coil, Macaulay, you have Faraday's law that says you get an induced voltage in a coil when the current's changing. Yeah. So
Yeah.
when we turn the transistor off, we've got this. Well, while the transistor's on, we've got this magnetic field built up in the relay coil. Yeah. When we turn it off, immediately you get it's an attempt to turn the current all the way off. You get a very rapid change in current. That would induce a very big, relatively big voltage in the relay coil. And by Lenz's law, that voltage opposes the change. So it tries to keep the current going. And what it does is, would attempt, under normal circumstances, to send a large current down that way through the transistor and possibly destroy it. So what they do is they have this flywheel diode that takes that current and dissipates it back through the relay coil in this circle around here. Yeah. So that this diode, remember, if you look at it, it's reverse biased to normal current, so nothing can flow down that way. We get this reverse current in here, and it just dissipates, takes that energy away from the relay, stops it going down through other sensitive components. All right? And I picked that diagram so that I could explain what's meant by a flywheel diode. You might see them on drawings and not understand why they're there. All right? Everybody okay with that?
Yeah.
Yeah.
Yeah. So, transistor as a switch. Example number 1. Using the transistor values from the previous tutorial, i.e. beta is 200, IC 4 milliamps, IB 20 microamps. Find the value of base emitter resistor, so that's this one in here, required to switch the load fully on when the input terminal exceeds 2.5 volts. So we've got 2.5 volts here. What value of resistor do we need in there to make sure that transistor turns on? We calculated IB in a previous example, it's 20 microamps. How can I start on that problem?
Hello?
Hello?
Did anyone else freeze there?
I froze a little bit, yeah.
Oh, I completely shut mine down and then restarted it.
Oh no, I didn't freeze that bad. Okay, using the transistor values. Would it not just be we'd have to do the input voltage minus the 0.7.
Yeah, yes, you're heading in the right direction. We had the formula before. IB was equal to V in minus B base emitter over RB. Yeah. So therefore we can say RB is V in minus BBE over IB. So rearranging that formula, yeah. So that's what you said, Diamond, up 2.5. Take away 0.7 for a silicon transistor. Yeah. Divided by 20 times 10 to the minus 6.
.09.
Nope.
Oh, never mind. Oh wait, no, that's plus. Wait, one sec.
Has a 9 in it.
90,000. A little bit off.
90 kilohms. Right now, I'm going to ask you another question now. I'm going to say that, remember we looked at preferred value resistors before. The two nearest to that are, so you can choose either 91K or 82K from the preferred resistor values. Which would you choose?
91.
91.
Anyone else?
I bet it's 82, right?
The other one.
Why are you saying 91?
Because it's a greater value, actually.
What's a greater value going to do to the RB current?
Kaboom.
Gonna F it.
No, just think about it.
Just take it down.
The current would drop. Therefore, what would happen to the overall VBE voltage?
It would drop as well.
Yeah, we must remember that we need at least 20 microamps to flow. Therefore, we would choose, would we not, the lower value. So we got at least, we must be absolutely certain that we're going to be in that saturation zone when we shut off. So we don't want a lower than calculated current. We want to go for the slightly higher calculated current, which would come from having the 82K resistor. It's the correct one to choose. Yep.
Perfect.
So we'd use 82K for those reasons. Because then you're going to guarantee you're going to have slightly more than 20 microamps flowing, and therefore you're definitely going to be in the saturation zone when you turn a transistor on. Yeah.
Yeah.
Okay, next page. 5 minutes. Have a go at that one, and then we'll go through it.
When we're all done, should we all crack open a cold one?
I'll tell you what, crack open a cold one, and we'll reconvene at 10 minutes to 4 with you having the answer to this problem. All right?
All right, cool.
I'm going to pause the recording now.
I'll go get a cold one.
So using the same values from previous examples, we want a load requires a current of 200 milliamps, IC 200 milliamps then. I'm going to input 5 volts and go calculate what the new value of RB is required. Yeah. So what do we need to calculate first? Because we know that RB is equal to V in minus V base emitter over IB. Yep.
Yeah.
Therefore, what do we need to calculate so that we can use that formula?
We need to do 5 minus 0.7.
Yep.
Over IB, but I wasn't sure where to get IB.
Well, if you remember, this transistor says uses the values from before, so beta is 200. Yeah.
Yeah.
So we know that beta is IC over IB. Therefore, IB is IC, which is 200 times 10 to the minus 3 over 200. Equals 1 milliamp. So now we've got that, we can plug that into this formula up here. So RB, the value of RB is V in 5 minus 0.7, all divided by 1 times 10 to the minus 3.
4,300.
Yeah, 4.3 kilo ohms. But that is an exact preferred value, so you would use that. Okay. Well, happy with that. So changing the input from the previous example, where it was 2.5 volts, to having it as 5 volts, but keeping the other conditions the same. We need a lower value resistor. Yeah. Our current's much higher, see? All right. Everybody happy?
Yep.
Yeah.
Yeah.
Right. Good. So just to summarize this transistor as a switch thing, I spent quite a bit of time on. But to summarize, transistor switches can be used to switch and control lamps, relays, or even motors. When using the bipolar transistor as a switch, you must either use it set up to working fully off or fully on. So we don't really want to be anywhere halfway in between those two limits. Transistors that are fully on are said to be in their saturation region. Transistors fully off are in their cutoff region. When using the transistor as a switch, a small base current controls a much larger collector load current. And when using transistors to switch inductive loads such as relays, solenoids, you'd have a flywheel diode. The purpose of that is to protect against the back EMF build up when the coil or solenoid is turned off. So they're the kind of main points as summary of what we've done up till now. Yep.
Gotcha.
So what we're going to do now is have a little bit of a briefer look at the junction field effect transistor. So a field effect transistor, a JFET in this case, voltage controlled 3-terminal unipolar semiconductor device, available in what's called N-channel or P-channel configurations. So we've seen that the bipolar transistor is a current operated device. We control the current going in at the base, and we do that, we control the current flowing through the collector. The field effect transistor, or FET for short, uses a voltage that is applied to their input terminal, which is called the gate, to control the current flowing through. The output current is proportional to the input voltage. So instead of being a current controlled device, they're a voltage controlled device. Yep.
Yep.
So there are different types of FET. With our bipolar transistors, we had NPN and PNP types. In the field effect transistors, we have what's called N-channel FETs and P-channel FETs. But then there's also two different overall types of FET. There's the junction FET or JFET, and an insulated gate field effect transistor, which is more commonly known as a metal oxide semiconductor field effect transistor. What a mouthful that is. So we use MOSFET for short. Okay. So we'll talk about JFETs and MOSFETs and forget about all those long words that they mean. Okay. So junction field effect transistor. What it has is a narrow piece of high resistivity semiconductor material forming a channel of either N or P-type silicon material. Okay, so that in the diagram there, you've got one that's got an N-type channel. That stretches between what's called the source and the drain terminals. And then there's a third electrical collection called the gate. Yeah, and it's in the N channel, the gate is P-type material. Okay. So we got PN junction between the gate and the main channel, effectively. So there's a little bit of a relationship between the terminals here. It's worth thinking about. In the bipolar transistor, we have the emitter, and the equivalent in the field effect transistor is the source. And then the base in the bipolar, the equivalent terminal is the gate on a FET, and the collector is equivalent to the drain on the FET. Yeah. Okay.
Yeah.
Good. So the symbols for the different devices shown. So we've got an N-channel JFET on the left, and it shows its construction. So you've got the N-channel sandwiched between the gate, which is two pieces of P-type material on either side, and then you've got the P-channel FET, which is the opposite. We've got an N-channel gate with a an N material for the gate, a P material for the channel. All right. What I'm going to get you to do is there's a link down the bottom of that page to another video about FETs, and it also covers the MOSFET as well, that we're not really going to go into in detail today. We'll do that next time. All right. So if you could have a look at that, I think it's about 10 minutes again. So if somebody let me know when you're finished, and then we'll continue from there. All right.
Oh yeah.
Oh yeah.
Gonna have
Cool.
to, could you post that link in the
And,
I'm back.
record?
Let's go.
let's go.
Oh, it's a share. Oh wait, no.
Right. So, how do we get on with that video, everybody? All right.
That's all right. Yeah.
Okay. So just a couple of more little bits to do, and then we'll probably have a little bit of time for me to answer some assignment questions. Output characteristics or voltage against current curves for a typical junction FET. So if you look at the top left-hand diagram, you've got volt drain to source across the bottom, and the current flowing through the drain ID on the left. And we got this pinch-off region down the bottom.
What the
That'll
hell?
be where the sorry.
Macaulay just got a question.
What's your question, Macaulay?
I haven't. I've just come back from watching that video.
Okay, sorry. Yeah, I thought you were already back. I'm sorry. All right.
Welcome back.
So that diagram again is showing you the voltage, drain source voltage versus drain current curves for different values of gate voltage. So the higher the gate voltage is, the less the maximum current is that you can have from drain to source. And then we've got these two regions again. You've got a pinch off region at the bottom got this region on the left, which is saturation. So if we were going to use an FET as a switch, then we'd want to work between the pinch off and a saturation region. So we'd be turning the gate fully off to get full current flow, and then we'd take it to the pinch off region to stop that current flow. Right, then characteristic curve. So we got an ohmic region. This is where V gate to source is 0. Depletion layer of the channel is very small, and this FET then acts like a voltage controlled resistor. So it's just like having a resistor, and the current will flow straight through it. Has a cutoff region, also known as the pinch off region, where gate voltage is sufficient to cause the FET to act as an open circuit. The channel resistance is a maximum. Yep, so switch off. And then we've got the active region, which is the bit in the middle. So it becomes a good conductor, and the value of the current is controlled by the voltage gate to source. All right, and then lastly, if you look at the right hand side of that diagram, where you get the point at the end where the current goes north very quickly, that's the breakdown region. It's where the VDS is high enough to cause the FET's resistive channel to break down, and you're in the realms of destroying the device if you get up there. Okay, so it's like having a bit similar to the breakdown voltage of a reverse bias diode. All right, everyone happy?
Yeah.
10-10.
Good. All right. So, drain current in the active region. I picked these out of some stuff that I found this morning. Didn't really take too much notice of them, but the drain current at any time is the maximum drain current times, I tell you what, I'm going to leave them till next week because I need to read them better. Sorry about that, boys. Note that the value of drain current between pinch off. Yeah. I need to check them out. Sorry. Oh, one thing we will say is there's, and we didn't really cover this with the junction transistors too deeply. I did, but we can have a common source configuration, which is like the equivalent of the common emitter that we already looked at with the BJTs earlier. Okay, so we got a common, the source connection is common to both the input and the output, and that configuration would be used in an amplifier. And then we got common gate. This is where the gate is connected to both the input and output, and it has generally used in high frequency circuits and where you want to impedance match. So you have a low impedance input, so where we want to match that and get the maximum power from a source, we can do that easily with that common gate configuration. And then the other one is that we can have a common drain. So here we got the drain connected to both. I would argue that. Yeah, yeah, that's this. Yeah, I would too. This drain's connected to VCC and nothing else. That looked like common source to me.
Definitely common.
Yeah. The one we're most interested in anyway is the first one, common source. All right. So what I'm going to do now as a special is have a look. We'll have a look at the assignment, and I will try and answer your questions on the assignment. Are you happy about me doing that?
More than happy.
Yeah.
Right. So just give me a minute to get the assignment up on the screen.
Well, outside like 160. All right.
Sorry, I missed that. My dog knocked my stuff off. What we doing now?
Our assignment.
I'm gonna try and answer some questions that you might have about the assignment, because you're due to hand it in next week, aren't you?
Okay, task 1A.
Hang on a minute.
So hypothetically speaking.
Hypothetically speaking, you want help with all of it.
No, well, not me, but can we focus on task 2?
What we can do is I'm going to go through and ask if anybody's got questions about each part of it. I think that's the fairest way to do it.
Yeah, I believe so.
My question is, I've sent an email twice. I've had no response. That's in regards to the other assignments. So I just wanted to check to see if you've got it.
Who was saying that?
Me, Logan.
Logan.
Yeah.
Yeah. You've had a response from Omal today, because I've seen it.
It's not come through to me yet. Maybe it's been delayed. I don't know.
You just come back with a.
I'll have a look. I'll have a look in a minute, Logan. I'll see if I can deal with that one for you as well. All right.
All right then.
Yeah.
I'm well sweaty.
Right. Share screen. Assignment. Share. All right. So, task 1. We got these 4 different heater configurations. So we got 3 heating elements, all 12 ohms each. We can connect them up 4 different ways. So you all understood that, yeah?
Yeah.
Yeah, task 1 was fine. 1A, 1B.
Anybody got any problems with task 1A or 1B?
No.
No?
No.
Right, 1C.
No. Okay.
Oh, well, actually, I've got a question.
Oh, let me get my assignment.
Because, well, now you're here, I might as well ask. So, for C, I worked out a total wattage of 64. Would I then divide that by 3 for each resistor and work and choose a heating element, or would I keep that? So I worked out the power of the whole circuit for the C, right?
Yeah, so you've got the power for
Dissipated. Yeah.
Yeah, you need to calculate the power dissipated for 1 heating element.
So that's 1 resistor.
Yes.
Okay. All right. Yep.
And
that's all.
The configuration. It says calculate it for configuration RH4 because that's the one that's in parallel.
Yeah.
And therefore, that's the one that will have the highest overall power. Yeah.
Okay. Yeah. No, I just wanted to make sure it was for 1 resistor.
Okay. Everyone else all right with that?
Yeah.
Yeah.
Part D.
I'm okay.
The D.
Taylor's getting it. Oh no, Jake.
I've been here the whole time.
Yeah. All right then. Okay, so.
I just had myself muted. That's all.
Yeah, I bet.
Anyone got any issues with task 1, part D?
No.
Mac has got a copy.
Anyone else?
Next.
Next, yeah. Part E.
I haven't actually looked at that one yet, to be honest. So, would you be able to give a brief overview?
Okay, so what you've done in the earlier part is you've done some calculations for, so in this part little IV here, we changed from the RH4 heater bank to the RH1, and then all other resistor values remain as calculated in parts 1 and 2. So you keep the 0.4 ohms of R1.
Jake, I hate to be a pain. Would we be able to mute your
Jake,
mic?
can you turn your speaker off, please? Or your mic.
Thank you.
Value you calculated for R2 and R3 would all stay the same. So then you've got to recalculate new values for I1, I2, and I3 to get a revised value of power for the RH1 heater bank configuration.
Wait, is this part of E? Has this got something to do with E?
Yeah, because up here, you calculated the power dissipated. You calculated the current I2. You will have done. If you haven't done it yet, you won't have. Once you know I2, you can calculate the value for R3 resistor. Yeah. And therefore, you can find I3, which is the current through the load. And therefore, you can find the power dissipated in these resistors, R1, R2, and R3. Yeah.
Yeah.
Then, what it's saying is, that's all with the highest power heater bank configuration connected, RH4. Yeah.
All right.
Then you're going to connect the lowest power heater bank configuration, RH1, because that's got all the elements in series, right? And then you're going to keep the same value for R3, R2, and R1, but recalculate new values for the 3 currents because they will change. And therefore, you can recalculate the power for the RH1 heater bank configuration. It will not be the same as what you calculated up here in part B.
Right.
Yeah?
Yeah.
And then the last part is, if you use Thevenin's theorem to determine the Thevenin's equivalent circuit, right, you'll then end up with a circuit that is just.
Yeah, I had a question.
Yeah, go on, Jake. Sorry.
There's that, you know, that 16 volts that's across R3 and RH4 above.
Yeah.
What are you supposed to label? Can I label that whatever I want, or because I've written a formula and I've just labeled it VR4. Is that right?
Yeah. In this diagram, in the figure 4.
Yeah, and if you scroll up a little bit more, there's that other diagram in part I. It says at 16 volts across RH4.
Yeah.
Yes.
Yeah, I've labelled that VR4. Is that all right?
Yeah, that's fine. Yeah, that's fine.
Okay. Right then.
I mean, this RH4 here is effectively the load.
Yeah.
Isn't it? So you could call it VL as long as you call it something that you haven't already used. Doesn't really matter what you call it. Yeah. It's the output voltage. All right. you want it to be 16 volts for RH4, it wouldn't be 16 volts for the others because the conditions will change. This current will change. Yeah. So part A is asking you then to go on and use the Thevenin's process on this circuit. So remember what Thevenin's is. You disconnect the load resistance, which would be this resistor here, leave two open terminals A and B, and then you calculate the open terminal voltage, and you calculate the resistance looking back in here.
Yeah, I think we have a handout that's literally identical to that question. Quite close, anyway.
Exactly.
That will help,
We've certainly done examples.
Yeah.
What you'll then end up with is the circuit that is got one voltage source. It won't be 24 volts, it'll be a different value. One series resistance, and your two terminals A and B that you can then connect any one of your heater banks in and do your calculations. So use your Thevenin's equivalent circuit to analyze the load current and power for each of the four load configurations, RH1 to RH4. And you can do that very quickly because it becomes a voltage divider circuit with one voltage, two resistances, and one current. Remember doing that?
Yeah.
Yeah.
Yeah?
Yeah.
Any more questions about task one?
Nope.
Goody, goody. Right. So we move on to task two, yeah?
Yeah.
Right. Any questions about part A?
Yeah.
What's that thing, Connor?
Where do I start?
Yeah.
Okay. So part one, so A1 is sketch a fully labeled phasor diagram showing the relationship between the current I and the three voltages Vs, which is the supply voltage, VL, which is the voltage across the inductor, and VR, which would be the voltage across the resistor. Yeah?
Yeah.
So what do we know? First of all, the clue in there is one current. So that's going to be a reference phasor. You're going to fix that at 0 degrees. So you're going to draw that left to right on your diagram. You've got loads of examples of these in your notes.
Does it need to have the values in?
Oh no, you're just sketching it because what I want to see that you know is the relationship, how the phasor, how the supply voltage is made up of the resultant of the two VL and VR voltages.
Okay.
Yeah, because I've just done my drawings on AutoCAD. Obviously, I can't scan them in.
Yeah, I've done them on Word. I haven't actually drawn it on paper. I've just done it on Word.
Yeah.
Is that right?
Well, you can. I don't mind how you get them into your report. Really, doesn't matter. You can draw them in anything and then just take a screenshot or something.
Yeah.
Yeah. So when it says sketch, it doesn't mean draw it to scale. But don't do them too small. I need to be able to see,
Yeah, I've done them huge.
What you're drawing. All right. So you're then going to put on that the three voltages Vs, VL, and VR. One of them is in phase with the current. Yeah. One of them's 90 degrees out of phase, either positive or negative. That's for you to find out. I'm not going to. And then Vs will be the phasor addition of those two. So you'll complete the parallelogram between VR and Vs. You'll draw Vs across the diagonal. And you have a number of examples of similar phasor diagrams in the notes.
what was the name of the notes, the set of notes that where we done that? Was it oh, where is it? Got it here somewhere.
Series RL circuits.
Yes.
Where's that? I ain't got that one.
I'll be capacitors and inductors in AC circuits.
Ah, yeah, sorry, yeah, I've got that one.
And all the stuff is on Moodle as well. All the videos are up to date and everything.
Yeah.
How good they are is another matter, but they're all there. Everything
Well,
I've got is there.
For task 2A-V, calculate the supply voltage in polar form. Is that with 200 hertz or 150 hertz as stated in IR?
You skipped a few things there, haven't you?
You have 200.
With 200.
Yeah. Right. I think I changed my mind there for some reason. Accordion didn't change it in the question, but changed it on the diagram. So we go what's on the diagram, 200 hertz. Yeah. So everybody okay with the second part? Current flowing. We're using the fact that you've been given 32 volts across the resistor and 8 ohms. Calculate the current. Yeah.
Yeah.
Supply voltage is a frequency of that should read 200 hertz. Calculate the inductive reactance of the inductor. So anybody got a problem with that?
No.
What you're saying is it should be the frequency of 250 hertz or 150 hertz. Which one?
200 hertz.
Yeah, okay.
What's on the diagram?
All right.
Taylor, yeah?
Oh, so I need to change it because I've done it at 150.
It's, yeah, it says 150 in the question.
Wait a minute. Whichever one you're done it with, we'll leave it at that, right? Don't worry about it. So don't worry about changing it. If you've done 150, leave it 150. If you've done 200, leave it 200. All right.
Right.
I can't say fairer than that, can I?
No.
Nah, but
No. Good. Right. So you can use Ohm's law to calculate the current. Yeah. And then you can calculate the inductive reactance. Either way, whatever the frequency is, you've got the formula in the notes for that. Nothing too difficult. And then you can use Ohm's law to calculate the voltages across both the inductor, and then you can add the two voltages together to get the supply voltage. Yeah.
Yeah, that's fine.
Okay.
What
So
about
that's
the
part
polar
A. Sorry?
What about the polar form part?
The what?
For 5.
Well, you're going to have a voltage. You've got a voltage across the resistor that is 32 volts at 0 degrees. You've been given that. Yeah?
Oh yeah, yeah.
The current will be angle 0 because it will be in phase with this resistor voltage.
Yeah.
But your inductor will not be angle 0 degrees. So you've got to use. I'm suggesting there that you use complex numbers.
Yeah.
Yeah.
Okay.
In either polar or rectangular form and convert between the two as necessary.
Polar.
All right. But you want what I'm saying there is I want the final answer, not in rectangular form, but in polar form.
Yeah.
Okay.
because if you're going to add two voltages together, to these two voltages here, VL and VR together, probably going to do that in rectangular form. What I'm saying is, I want the answer converted to polar form.
Right.
Need a wee.
Then we're adding a capacitor to this circuit. So got the same inductor, same resistor, 12 microfarad capacitor. Any questions about part B?
No.
No?
I mean,
Anyone
well,
else?
just like everything.
I haven't done it, so
Yeah, I haven't done it either, to be honest.
Well, you've got the formulas in your notes for
No, I see
calculating the
circuit that
capacitor.
one.
Yeah, calculating the capacitive reactance. Yeah.
Yep.
yeah. What's the
And
name
then
of the notes we had for that one?
Same notes.
Is it the same one?
same notes.
Okay.
Yeah.
Oh yeah. Week 5.
Capacitors and inductors in AC circuits.
Yeah.
All right.
Yeah.
So you'll then have is you'll have a resistance, an inductive reactance from part A, and a capacitive reactance from part B. So you must use the same frequency for both part A and part B. Whichever one you've chosen and used for part A, you've got to use the same one for part B.
Yeah.
All right. You've got to show the relationship. So again, there's plenty of examples in those notes of how to draw that relationship between the impedance diagram, and what's meant by the overall reactance, which is the difference between the capacitive and inductive reactance. Remember, they work 180 degrees opposite to each other, and then show the resultant phasor, which is the overall impedance Z. And again, that's just a sketch, but it needs to be correctly labeled, okay, drawn nice and big to show those relationships. The one thing you want to be clear about is, in terms of that being a sketch, it doesn't need to be a scale, but should reflect which one of the capacitive and inductive reactances is bigger than the other. It's quite important to show that difference.
All right.
All right.
Yeah.
You can calculate the total impedance of the circuit. You've got the formulae to do that in your notes. Again, you'll be working with complex numbers. Then it's giving you a current, so it's saying if a current flowing is measured to be 5 amps at angle 0, so it's a complex current, but it's fixing it at angle 0 as the reference phasor. Calculate the supply voltage Vs. So again, that's Ohm's law, just for complex numbers. And then lastly, once you've got the current, you can calculate the volt drops across the resistor, the inductor, and the capacitor, all in polar form. All right?
Yeah.
And that voltage across the resistor won't be the same as it was in the example A, because the overall impedance of the circuit has changed.
Okay.
All right. Everybody happy with that? Any more questions about task 2, part B?
Nah. Thank you.
Good. Right. Second, part C is parallel. So that's the next set of notes that you had. That's called AC parallel circuits.
Yeah, week 6, I think.
Yeah, that's the one. All right. So here you've got the representation of a coil like a coil of wire, like a solenoid coil, that's got inductance in series with its resistance. And we got a current I coil flowing through that. And that's in parallel with a capacitor. So we got IC flowing in the capacitor. So we're in a parallel circuit situation where IS, the current drawn from the supply, is the sum of these two currents by Kirchhoff's current law. Yeah?
Yeah.
60 volts, frequency 250 hertz. All right. So, any particular questions about that, or have nobody attempted that question yet?
I haven't attempted it personally.
No.
Yeah, just
Anybody attempted it?
Just hypothetically speaking, on a 60 volt power supply with 250 hertz frequency input and 40 millihenry inductor with a 4 ohm resistor in parallel with a 18 microfarad capacitor, how would I calculate the current in polar form? Just hypothetically.
What's the part 3?
Aye.
Well, the kind of the steps that I've given you from 1 to 5, I to V, actually take you through what you need to do in a way, because the first thing you've got to do is try and calculate at least one of those currents. Now you can calculate the impedance of the coil is the resistance and the inductive reactance added together, but they're going to be complex, aren't they? Because your resistor's got no angle associated with it. You've got the formula for the total impedance of that coil in your notes. Yeah.
Yeah.
Then you're being asked to calculate the current. So once you know the total impedance of the coil, you can then use Ohm's law with the complex numbers to calculate the current I coil. Yeah.
I'll work my way through it.
Part 3, if you calculate the capacitive reactance, XC, you can then again use Ohm's law with the applied 60 volts to calculate the capacitive current, IC. Yeah?
Yeah.
Then you can calculate the total impedance of the circuit, ZT, and find the supply current. So you can do a parallel on Z coil and ZC to calculate the total impedance, ZT, and then use that with the voltage to calculate IS. And then what the last part is asking you to do is to check that result or check your results comply with Kirchhoff's current law. So what you've got to do is add the two complex values, I coil and IC, together and show that you get the same value for IS. As you got in part 4. Yeah?
Yeah.
All right. They're, like many of these things, there's always usually at least 2 ways you can go about it, and one is always the check of the other. Yeah?
Yeah.
Right, any more questions about part C?
I just don't know anymore.
Okay?
No,
Yeah,
no.
good.
Right. Anybody attempted part D?
I've done it.
Yeah, I'm all finished, I think.
On that one, yeah?
Yeah.
Yeah.
I mean,
Dom has got a question about III, I think.
Which one, sorry?
III.
I.
Do I?
3.
Might do. Have a look. No, I think I think we managed to do that one.
Because down
no,
in part
IV.
5,
IV, I mean, with the voltage being high.
Oh, right. Yeah, so just like roughly, what sort of voltages are we looking for? What is considered quite high?
will you tell me what you got?
About 1,662.747, just roughly.
Oh, we got just roughly.
Yeah.
I haven't got the answers in front of me, but that's not necessarily the right. Have you got the same value for VC as you got for VL?
It was just slightly
Mine's
out.
close enough. Yeah, mine's not.
Yeah,
Mine's not
within
identical.
a volt or two because
Yeah,
of
yeah,
rounding. Yeah?
Yeah.
So that's a good sign.
It
Because
just seems high.
Yeah, but remember, because you're inputting 375 volts and you're getting thousands and more volts across the components. But remember what resonance means.
Yeah, I don't
At
really know what it means.
resonance. Sorry?
I don't really know what it means.
You do know. You don't.
No. Well, I can't
Well,
remember.
any circuit like this has a particular frequency that would be its series resonant frequency. Yeah?
Yeah.
And at that frequency, the reactance, the size of the reactance of these two components, L and C, are exactly the same. So if you calculate, I'm gonna turn it into an example where I'm gonna pick some figures. At resonance, if the XL was 1,000 ohms, XC would also be 1,000 ohms. But the trick is that XL's got a positive 90-degree angle and XC a negative 90-degree angle, so they effectively cancel out at resonance. Yeah. So
Right.
the only impedance left at resonance is the resistor. Therefore, at resonance, the overall impedance is as low as that's going to be, and therefore the current's going to be its highest.
Okay.
So at resonance, you get potential for very high voltages across these two reactive components. And with 375 volts being the supply voltage and only 8 ohms resistance, 1,000 and more volts is not out of the way.
Right.
But in the last bit, you're asked to compare the results you get there with what you got at the other frequency in part B.
Yeah, I haven't done part B first, so.
Yeah, that's quite strange that you've done that part first and left this part till afterwards. It doesn't matter as such, but that's a bit of a strange way to go around doing it, really.
It's strange, Dom.
I wonder who thought of that.
Yeah.
Cool. All right, well, that's
Okay.
cleared up a fair few things.
Mike,
Yeah.
do you know if we've got Omar later today? Because I haven't heard anything.
As far as I know, we had a meeting yesterday, and he didn't say to me that you wouldn't be convening today, so I'm assuming that you are. Has he sent you no details?
No.
I haven't heard nothing, no. What time's his lesson normally?
Well, we'd normally finish at 5:15, so I would assume he start at 5:30. I don't know.
Yeah, that is it.
Yeah,
Okay,
5:30.
He hasn't emailed or anything. I haven't got any details about joining.
I thought I had an email from him yesterday.
Yeah, that was just about behaviour. That was all.
Mac has been playing up.
There's nothing on there about what class we're joining or anything.
That is true. I assumed that was the one, but it's not.
Yeah.
Am
I'd
I okay
suggest
to
you
make
just
tea or
fire him a
not?
quick email, one of you or more than one of you. Just fire him an email and check. But he certainly never said anything to me about not having a session. So I would have thought he would have told me. Any more questions about the assignment?
No.
Not at this stage. Obviously, task 2, I've still got to go through it, so I may have some questions. So I may have to email.
Yeah, okay.
But so
Well,
now,
my formal work days for answering email are Tuesday to Thursday. If outside of that, you might be lucky to get an answer, but
right,
you
that's
might
fine.
not. All right. Yeah.
Yeah.
All right. I just want to have a want to speak with Logan if he's still about. He isn't.
He is.
Is he?
Nah.
That's all right. I'll email him then.
All right.
If you're finished with questions, we're finished there for today, and
All right.
we'll
Thank you.
reconvene next week on
pleasure.
at Upper State. Yeah. Okay.
See you next week.
See you next week.
Bye.
Bye.
Bye.